So I would like to thank everyone for coming and organizer, specifically Victor, for inviting me. It's a really nice workshop. So I indeed was asked to talk about this topic, and there is an interesting story about it. I was actually the only one in collaboration who wanted to change the name because I thought dynamical phase transition is too generic, so we have to be more specific. But I was outvoted by these two gentlemen, so Stefan Karain and Markus Heil. And I have to admit that I was heavily involved in that work, but after that I moved to other subjects. So I apologize, I didn't follow even all the literature on this subject. So I thought, given that also there is another experimental talk by Klaus, I believe, who should be able to tell about more recent developments and, of course, most importantly, experimental developments, I thought that instead of trying to catch up with all the literature which appeared in the last 4 years, I will sort of give an overview and maybe mention some interpretations which we didn't really follow and which I think are interesting to follow. So at the end, I probably will not use all the time for this talk. So at the end, I thought I will also talk very briefly about another work which was done in collaboration with Vladimir Gitsev on sort of integrable flow K-dynamics, because I think it's related also to the topic of this workshop. So essentially, the talk consists of a main part and a shorter part, if I get there. OK. So I apologize in advance if I really miss some important paper. So let me remind you about equilibrium Young-Lee or Fisher zeros, because they will play a crucial role in the rest of the talk. So let me take equilibrium. It doesn't matter if it's quantum or classical. Just for diversity, I thought that maybe I'll show a classical partition function. So, and well, we know very well what it is. And then we know that this partition function is nothing but a generator of moments of the interaction energy in your model. And the log of this partition function is free energy, which is generator of cumulants. And then one thing we know about phase transitions, and many things can apply to first-order phase transitions, but in this talk, I'm only focusing on second-order phase transitions. So we just didn't think much about what happens in first-order transitions with dynamical phase transitions, so I don't want to talk much about them. So we know that free energy becomes a non-analytic function of temperature or tuning parameter or something else. And in particular, this high temperature expansion breaks down, because high temperature expansion, of course, is fully analytic same temperature. And there was an extremely nice work by Ling and Yang, who sort of understood this non-analyticity through condensation of zeros of the partition function. So let me just show this very simple model, Ising model, and Li Yang originally considered model in the magnetic field. So, and then if you think about this partition function, it's actually polynomial in this guy z, which is exponent of 2 minus 2 beta h. It's more or less clear, because if you sum over all spin configuration, each spin either comes with either +1 as positive number, negative number, plus minus 1. So we will always, each term in the partition function is product of this many z's. So, and then because it's polynomial, we can, of course, write it as a product, and it's defined by its roots. And then there is a sort of nice observation that, well, partition function is real and positive by construction, right? So it means that you cannot have roots on real physical plane, right? This is, if you think about physical magnetic field and physical temperature, they're all real. The real partition function is a positive number. So it means that all zeros should be in the complex plane. But then they realized that, on the other hand, we know at phase transitions, Taylor expansion breaks down. So the way to explain it is to assume that the zeros somehow go very close to the real axis. And then some years later, there was a very similar idea by Michael Fisher. he said that, well, we actually even don't need to consider magnetic field. Let's just consider complex temperature. And the idea is exactly the same. So if you look into partition function, now it's a polynomial of these guys, exponentials of minus 2 beta j. Same story, polynomials have zeros. At the phase transitions, we should have singularity, so zeros should condense. And this is some numerical simulations from 84. So S, I forgot exactly what it is. It's, I think, sinh of beta j or something like that. So real S means physical axis, imaginary S means unphysical axis. It's like if you want imaginary temperature. And then if you look into a structure of zeros, that's exactly what I think Fisher and Lin Yang thought about. We have one phase, the high temperature phase, where everything is nice. We have analytic function. Well, free energy is analytic function. Z is positive, right? Log of Z is also nicely behaved. But once we go to the phase transitions, we start to see like there are these zeros. Good. Now let me go a little bit to the side of interpretation, because complex temperature is nice, but that's unphysical. So let me try to connect it, if you want, with large deviation theory and say it's actually physical, it's measurable. And of course, we know complex temperature is time. So, and I'll try to explain now in which sense complex temperature is time in this setup. So let's look now in imaginary time partition function, Z of just IT. Well, by construction, it's just trace of e to the minus IHT. That's the definition, right? So now we can write trace in any basis, but let's just go to the basis of the Hamiltonian. Then this trace is particularly simple, and it's just sum of these oscillating exponents. But now let's do the same trick as we always do in thermodynamics. We just separate the sum of states to sum over energy shells. I didn't write it down, but it's clear what's going on. Then we can write the sum as an integral over the energy. We have still e to the minus IET. And then we have density of states. So how many states we have within each energy shell. So we see that complex temperature partition function is just a Fourier transform of the density of states. Well, now we can add extra ingredients. So we have just so far purely imaginary temperature. Let's add real temperature as well. And let's repeat the same game. So we also write formally what the Z is. We go to this eigenbasis, and now we see that, well, we still have this e to the minus e and t. But then we have this extra exponent, which looks almost like a Boltzmann distribution, right? And it is a Boltzmann distribution if we divide it by partition function and multiply by partition function. And then what we realize, cut off a little bit, that what we have is Fourier transform, not of density of states, but of energy distribution, right? Because if we take this Boltzmann weight and multiply by density of states, we will get the probability of having energy E. So we see that in some sense, there is nothing mysterious about complex temperature. It's just sort of just Fourier transform. There is one problem with that, and that's why probably it was not observed for a long time, is that as I showed in the previous graph, transition happens at non-extensive times. But on the other hand, for phase transitions, we want extensive energies. And now we see, well, that's a crazy thing, right? It's just crazily oscillating thing times something which is peaked at extensive energies. So we see that this is going to be exponentially small. So actually what we are dealing is, we are dealing with a large deviation functional, really. And when we talk about zeros of complex Z, which is the same as singularity in complex F, which is log of Z, this is not singular, we actually talk about large deviation theory. And sometimes it happens in thermodynamics that even though we are analyzing large deviation functional, we can extract information about equilibrium phase transitions if we can access this functional. Good, this is still equilibrium, but let me now go to same object, but now let me give try to give non-equilibrium interpretation. So instead of energy, I want to operate with work. So if I want to have work, I want to imagine that I'm doing some quench. And let me imagine that I'm doing a very simple quench. I start from a Hamiltonian 0. So it basically means I start from completely random state, and there is no energy cost associated with it. Then I quench to some Hamiltonian HF, and then it's more or less clear that energy and work are the same. So I'm just changing labels, but let me just still go through this calculation. Now ask, what's the probability of doing work? Well, it's given by the sum of an initial probability to occupied state M of my 0 Hamiltonian. Good thing I can use any basis for this. Then I have probability to make transition from state M to state N, which is like an overlap squared. And then I have a delta function, which tells me that energy change, which is work, is exactly equal to energy difference. Then I notice that if I start from a flat distribution, so infinite temperature, this drops out. It's a constant, 1 over z. Now I can sum over m. This is identity, right? It's completeness relation. So I can remove, oh, I think I messed up I and f, so this should be final. This is initial. Anyway, initial is 0, so I'm dropping index final. So I get what I want. I get my probability of work, which is the same as probability of energy. Okay. So I just see that now my complex temperature partition function, again, complex imaginary, I would say, temperature partition function, is a Fourier transform of the work distribution. So, and finally, I can make my time complex. So for the same quench, I start from infinite temperature, 0 Hamiltonian, but I make time complex. Same exercise. You can say it's a Laplace transform, but also, and this will become important somewhere later in the talk, I can view this tau as a post-selected temperature. It's again interpretation. So what I'm doing, I have work distribution, P of W. Then I skew it by exponent. So basically, I suppress, if you want, I take my experimental work distribution, I multiply it by exponent, cutting off all large works. So I get skewed distribution, and I take its Fourier transform, and then I get my z at complex temperature. Okay. So why I'm doing? Well, when tau becomes very big, I'm projecting to the ground state. So let me just summarize this part, and I'll go to non-equilibrium. So I just told you that complex temperature partition function, and I switch from tau to beta to highlight its really initial temperature, is just a Fourier transform of energy distribution. And beta is just my equilibrium temperature. On the other hand, the same object is given by a Fourier transform of my work distribution in the sense I described. And tau, you can view tau as a post-selected temperature. It's just interpretation. Well, now we can generalize it. Of course, it's not the way we came up with this. It was just random walk. Still remember it, Stefan was visiting me at BU, and he was complaining that Mathematica was producing some crap. He was just computing a simple object, Loschmidt-Echo, in a simple model, transversal Ising, and there was just some crazy stuff, and that's how it started. It has nothing to do with this. But the way I'm trying to present it is that there is actually a direct connection. It's not just similar, what I'm going to describe to Fisher zeros. There is a direct connection. So now I can define this object, which almost looks like Loschmidt-Echo, and or return amplitude. Echo is this squared. Anyway, so it's expectation value of 2 exponents. Now I have some initial Hamiltonian, which is not 0. So I extended there. And I have final Hamiltonian, which is still h. I can still have some finite temperature beta of my initial state. And then I can have complex T. So let me look at this object, what it is. So if we want its weighted sum of return amplitudes. So, well, again, I can say it's sum of all initial states with this Gibbs distribution characterized by beta. I have overlap initial and final state, and I have this Fourier transform. But if you just stare at this carefully, this is nothing but Fourier transform of the work distribution. So this object is exactly the same as this object. So I see that there is a natural generalization of this partition function, which now doesn't have equilibrium meaning, because I have initial Hamiltonian, final Hamiltonian, but it's a sort of a natural extension of this partition function. And now, well, this object I don't think was ever studied. But what one can do is to take the limit when beta, so initial temperature, goes to infinity, so I'm in the ground state. This statement didn't care about beta, but now my L of infinity and T becomes really return amplitude, right? Because now I'm taking weight with respect to the ground state. And this is, I'll call it Loschmidt echo, even though it's square root of Loschmidt echo, but that's somehow this terminology stuck. So we see that Loschmidt echo is indeed Fourier transform of the work distribution. And actually, Sandra Silva was first to realize this, I think. And this is a natural non-equilibrium extension of the complex temperature partition function. Good. So now that's yet another summary of what I was trying to say, is that we have a continuous line between normal, if you want Fisher zero, so normal complex temperature partition function, and Loschmidt echo. Continuous line in a sense that on this side where initial Hamiltonian is 0, I'm always studying the same object, Fourier transform of the work distribution. It's the same, it's the same object I'm studying everywhere in this line. But if I look into this point where initial Hamiltonian is 0, then this is just my equilibrium partition function. If I look into this point where initial Hamiltonian is 0, and you might think about the temperature also changes in this line, so I'm starting from the ground state instead of starting from infinite temperature, I'm getting a Loschmidt echo. And complex time, in both cases, equilibrium or not, we can view as sort of post-selected work probability distribution. OK, so now that's a definition. Now it becomes more natural, because this object, as I said, it's sort of the same on both ends. So we can define zeros of the Loschmidt echo and call them dynamical phase transitions. So we can view, in simple words, equilibrium phase transitions as a breakdown of high temperature expansion, and dynamical phase transitions as breakdown of short time expansion. And let me show this original simple work. It's actually great to analyze simple models if results turn out to be general, and when we were working on this, I'll just show explanations we had kind of didn't imply that this is really general. But anyway. So this is a transverse field Ising model, which probably everyone is familiar with by now. So it has transverse field, spin-spin interactions, and it has a critical point when this coupling G is equal to 1. And what we are doing quenches. We're doing them both within one phase and across the phase transition. And we're studying exactly this return amplitude or Loschmidt echo as a function of complex time, so Z. So, and that's the result of this numerical simulation. So what's plotted are the zeros of this L of Z, or singularities of F. So vertical axis will be my real time. So it's time after quench. Imaginary axis will be like a temperature now. But we are considering quenches, so this is, if you want, experimental axis. This is more subtle axis. And then we see, so yeah, and sorry, experimental axis is t equals to 0, so it's this one here and this one here. So A shows when we do quench, zeros when we do quench within one phase. And when we do one phase on this our physical axis, nothing happens. So it actually means that if we study our free energy, large deviation functional if you want, it's completely analytic. So if you want to study what's going on here, in principle, you can just study a short time expansion, perturbatively analytically continue, and you are done. On the other hand, if you do quench across the phase transition, you see a completely different structure. It's not the same as in equilibrium case, but it has the same feature. So these lines go all the way to infinity. So what you see that up to certain time, everything is OK, but beyond certain time, there is no analytic continuation. So Loschmidt-Echo becomes an analytic function, singular function. So one can do a little bit of analysis when it happens, and there are some formulas, but I'll probably try to just explain in words what goes on. So there is some emergent energy scale which has nothing to do with the gap. So I'm say, going across the phase transition. This energy scale is related, well, it's time scale and energy scale inversely proportional to each other. And energy scale is related to both initial and final coupling. And you can just convince yourself or trust me that this equation has solution only if G0 and G1 are on different sides of the phase transition. So there are some exponents which are not the same as equilibrium exponents, so they're emergent. Let me try to explain what goes on in this simple model. And as I said, this explanation kind of didn't imply that it's too generic, but it works. So this transfer field Ising model is very simple. It's a collection of two-level systems in momentum space. So, and then if you plot epsilon k as a function of g, usually we plot dispersion as a function of k. Here I fix k, so each curve corresponds to a fixed momentum and different coupling. So if I have a zero momentum, as a function of g, I have gapless point. This is my phase transition. If I take finite momentum, of course, gap never closes. So I have basically a collection of this Landau-Zehner problem. Then I do a quench, and then you can immediately see without any calculations what goes on. So if I am sitting on this branch, so my gap is very narrow, and by doing very fast quench, I actually transfer all the weight to excited state. On the other hand, if I sit on some high energy state, if I do a quench, well, I even didn't see the gap. My state is it's so high energy, then I don't care about coupling. So I still predominantly in the ground state. So you just see by continuity there should be a point where temperature is infinite, or I have 50-50 occupation. And now if you think about two-level system, if you have a spin 1/2 pointing up, and you rotate it exactly by pi/2, then at some point, so you create superposition of up and down, then at some point, you will create a state which points down, which is completely orthogonal to initial state.
Your question. So the phase transition is a specific moment of time?
Yes.
Or is it some time where something happens?
Non-electricity, yeah.
So then I follow up generic question. Suppose you have just some generic model where you do quench, and eventually you know if the system is going to thermalize.
Yeah. I'll come to it. It's large deviation phase transition. It's not, life would be too simple.
So then what you're defining is specific to integral models or non-integral models, or is that?
No, it doesn't matter at the end. That time we didn't know, but numerics shows it doesn't matter. I don't know how to prove it though. Okay, so now let me give completely, so that explanation really was based on integrability on this Landau-Zehner or whatever. Let me now give another explanation, which actually does not care whether the model is integrable or not. And this is probably more physical. So let me now look into the same problem, but from the point of view of not these two-level systems, weird fermions, but from the point of view of real spins. But let me take an extreme case when I start from zero coupling and go to very, very large coupling. So if I go to a very large coupling, I know what my evolution is. My evolution is just spin precession. Well, then I know what's going on. So spins will start to precess together. And then what I'm doing a weird thing. I'm projecting back to the ground state, which is either up or down. I actually have two ground states. Now, if spins precessed by angle which is less than pi/2, with exponentially large probability, I will project to up manifold. On the other hand, if my spin is precessed by angle more than pi/2, then with exponentially large probability, I will project to down manifold. And at the end, that's as simple as that. So the non-trivial thing in this picture that this is completely robust against like going to a finite magnetic field or different ground state. So, but at least this suggests, so in this explanation even doesn't care about dimensionality of the system. If you do an opposite thing, so if you start from a fully polarized and go to Ising, it becomes much harder. In 1D it's the same, you have duality. But in 2D, actually there was nice works by Markus Heil. He mapped it, he used RG in complex temperature plane and so on and so forth. Good. Well, this transition is not just transition, it's really topological transition. You can say pretty much anything about it because it's hard to observe, I guess. But in reality, why this integrability, non-integrability, and so on don't matter, the physical reason is kind of simple, because we are looking into such weird configurations which go back to the ground state. So basically throw out all generic stuff which led to heating. So large deviation can be a bit tricky. So I'll come to that, yeah. So let me now say that, and this is, I think, could be a very interesting experiment, at least in small systems it's probably possible. So let's look into some physical observable, like magnetization. And this would be something like a red line. And with this red line, you see hardly you see anything. And even though it's an integrable system, but you still, as you said, you have heating, which is not exactly thermal, but say GG. So you get some damped oscillations. So you won't see any singularity there. But now let me do the following thing. Let me actually do a similar thing as I said before. I'll cool by post-selection my state. I'll explain in the next slide or 2 slides after what I really mean. So mathematically, it just means that you propagate your wave function in imaginary time. Physically, it means that if the state has high energy, you just disregard it. So you analyze sigma z only if energy is small, smaller than some threshold. And this R kind of sets this threshold. And now, so we're doing exactly what we are forbidden to do. So like in any textbook, we had taught that you should be very careful. You shouldn't disregard data because it will skew your probability distribution and so on. But here I'm suggesting to do a completely opposite thing. I want to really disregard a lot of data and analyze only a small subset. So just these rare instances when we didn't have much heating. And then I plot exactly the same object, sigma z. And then you see it slowly develops more and more interesting features. And eventually it goes into kinks, which is completely consistent with explanation which I gave, because it's either all up or all down. Moreover, if you think about Loschmidt amplitude in this favorite, it's a complex number, k-dependent, you can define winding number and so on, you'll get integers. Yeah, I'll skip that. So, and finally, like with respect to post-selection, let me say that another potential way to observe it is to consider a slightly different setup when we do sort of a double quench. So imagine that we started coupling G naught, we did a quench to coupling G, we wait for some time t, and then we quench back. And now we ask, what's the probability of doing work as a function of the duration of this quench? And then I'll just keep all details. So it's clear that if we ask what's the probability of doing zero work in this setup, it's exactly like Loschmidt echo squared, because it's really a probability to come back to the ground state. So it actually means that we can introduce post-selection now in this way. We just sort of, you can introduce soft cutoff or hard cutoff. So you do this process, you measure the energy. Energy is above some threshold, you throw it out. Energy is below threshold, you keep it, and so on. So you actually filtered out all states which produced high energy. And then you look what's the probability of being below this work W. And then you see the same story. So if you increase the threshold, so it means you go to lower and lower energies, it becomes more and more singular. So in this sense, post-selected cooling is exactly like equilibrium cooling, when you can approach quantum phase transitions by cooling down. Here you cool down by post-selection, you also approach this quantum phase transition.
But if you have a chaotic system, you can never post-select, is that?
Sorry,
if you have a chaotic system, you can never post-select.
No, you just do double quench, you do a measurement. You cannot do it in a large system. because you have to throw out exponential amount of data. But if the system is reasonably small, I don't know, 10 sites, 15 sites, why not? You just measure energy. If energy is high, you give this, you just don't record your data.
But there is no sense of thermodynamic limit in these phase transitions.
Well, you always have a crossover, that's true. But if you have, like, I'll show you experiment in a second with 8 sites, and crossover is very sharp. It's almost like a transition. So there is another paper, short, and there were many other later. This is by Karashan and Dirk Schuich, who analyzed non-integrable model. I just don't want to go into details. They break integrability. They make sure they're far from integrability. They do very careful, I think DMRG, I forgot. But anyway, so they see very nice phase transitions. This peaks becomes not periodic. So apparently this simple cartoon is not exactly right. But they see if they quench across various phase transitions, they see peaks. There were many other works which even showed that these dynamical phase transitions might not be associated with real phase transition. But I don't think there is much understanding what they mean. So, and there were 2 experiments. One is by Klaus' group. So because he's giving a talk, I'm even not mentioning anything about it. There is another by, yes, not Vienna, Innsbruck, right? In Innsbruck, and they had a very small system. I think 8 sites or something like that. So with various, these are trapped ions. So this is a long-range interaction, so infinite range interactions, and they saw very nice transitions, as you see. So thermodynamic limit here is not a problem. So which actually tells you that experiments are possible. Okay, so the final thing I want to mention about this topic is that, well, recently people are interested in out-of-time correlation functions, and this is very simple and trivial observation that Loschmidt echo is actually out-of-time order correlation function. So in this sense, this is the same object. This is the same, oh, at least one example of this object. So these out-of-time correlation functions, they become very popular. My versions because they are not measurable, but maybe there are some other issues. But to be serious, it's actually Larkin introduced them long time to try to describe quantum chaos and connect it with Lyapunov exponents. And Victor actually had very nice paper recently showing this connection in more detail. But let's just say this is an interesting object. It's called out of time because time does not monotonically increase towards the center. So you have a correlation function like T0T or T0T0, something like that. So one can show that if you know the Schwinger-Keldysh formalism, so this type of functions cannot be represented in causal way. So any physical response is causal, right? So these correlation functions cannot appear in any physical response, like in any susceptibility. But it doesn't mean you cannot measure them. So, and let me say that Loschmidt echo, which also never appears in any physical response, actually is an example of this function. Moreover, Loschmidt echo actually can be measured if we have 2 copies of the system. And it's extremely similar to entanglement or any entropy. And there was a nice proposal by Peter Zoller group and Rudelli, I believe. And it was measured recently in Marcus Greiner group. So it's not the topic of this talk, so I'm skipping it. But essentially, if you have 2 copies of the system, Peter Zoller and Andrew came up with a very nice idea that if you interfere them, you can measure trace of product of density matrices. And if density matrices are evolved with slightly different Hamiltonians, this is exactly a Loschmidt echo. So these things can be measured also. They were not measured yet as far as I know, but I think it's interesting. So, and then it's, as I said, it's a trivial observation. If you look into square of Loschmidt echo, well, it's just expectation value of one exponent times expectation value of another exponent. Well, let me just be a little bit more fancy and introduce projection operator. So it's like P naught e to the minus P is projection to the ground state. exponent P naught, another exponent, another P naught. But then I can observe that this is either Heisenberg representation of P at time minus t, so I can write it formally as this guy, or I can add 2 exponents here and here. It's trace, it doesn't matter, and then I will get the same result, which is of this form, P of t, P of 0, P of t. Of course, usually projection operators are crazy, but let me point that for the ground states, projection operators are not completely crazy. These are kind of string operators, because we know projection operator is basically exponent of minus h. So it has, this product.
So if I understand correctly, the definition of this OTOC is based on local operators, right? Your projection operator.
Yeah, okay. It's out of time order correlation function. Maybe, I don't know if you come, maybe it's not OT. It's out of time order correlation function of this particular operator.
Right. So if you talk about chaos, they wanted to have local operators.
Well, if you want my honest opinion, I don't think they really know what they want. I mean, they just analyze local operator. They do Kitaev model, right, where there is nothing local. So it's not clear that, I don't know. Loschmidt-Echo definitely knows about chaos. No one questions that. So it means that this particular out-of-time order correlation function also knows about chaos.
But this won't be growing exponentially for chaotic systems.
Well, I don't want to speculate on this. I just showed what it does. It doesn't grow actually here in this. Initially it's 1, but you can probably subtract. Yes, it might grow exponentially or Gaussian. We focused on late times where you get the singularities. So this, actually, we never discussed this and we never thought about this because we wrote paper before this object became popular. But I thought it's kind of an observation which could be useful. I'm not that early, so I'll give summary of this part 1 and then spend maybe 5 more minutes, hopefully not more. So dynamical quantum phase transitions are natural extension of this Li-Yang or Fisher approach to equilibrium transitions. This Loschmidt-Echo is related to large deviation functional of the work distribution. Also, I mentioned about post-selection and so on. So these dynamical quantum phase transitions topological, I forgot there was a separate paper by Markus Heil who showed by the topological, they have winding numbers and so on. And they are not really limited to integrable systems or quenches. You can consider continuous protocols and so on. Of course, there is a big remaining question, what we really learn from them. So they exist, it's confirmed, they are even measured, but it's not that I know at least intuitive explanation of what if we see the phase transition in a known system, what we learn from this. And that's a question. Okay. Let me talk about a little bit integrable Floquet dynamics. There's a popular topic about time crystal. And time crystals, there are many of them. My favorite is this clock. So these are basically devices which spontaneously break time translational symmetry. And they can be realized only as transients. And of course, usual problem, like with this clock, that they dissipate energy. Or if you drive them, they heat up. And there are some very interesting exceptions, and I believe people will talk about them. So these time crystals which don't heat up. So one of the challenges is to reduce or eliminate dissipation. And here, if we look on the other hand, let me just now focus on Floquet theory, and I'll come back to more generic setups. So if you have a Floquet theory, well, since it's quick, I'm not going into details. Well, Gil will also give a talk, I guess, about Floquet system. So we have an emergent, looks like conservation law, which is a Floquet Hamiltonian, because we can say that this whole periodic sequence is a quench to a Floquet Hamiltonian. So it looks like we have emergent energy conservation, energy associated with H naught, and which should prevent heating. Of course, the trick is in details. So if we just have this quench that I showed before, I have X, which is H1, and Y is H2 with some constants, and we start writing what my Floquet Hamiltonian is, then I start generating a lot of mass. And no one, as far as I understand, even mathematics, knows how to deal with this series. It's believed they are asymptotic, but even this, I think, is not really rigorously proven. So there are possible ways out. A, we can drive at high frequencies. when T1 and T2 are short, then each term here is suppressed by power of T, and maybe coefficients here grow faster than exponential, so this is the asymptotic series. At least it should work for long times. And there are examples which I guess others will talk about, including MBL, where it's believed, I don't know if it's rigorously proven or not, but at least numerically, and there are some good arguments, it's believed that this is a convergent series. Well, another set of approach, and we also heard about them earlier, is that if we consider weak coupling to environment, we consider open systems, and then we stabilize this. And, well, MBL I already mentioned. So the idea, which sort of we had, and mostly it's Vladimir's work, I'm just a messenger here, that we can think about protocols which approximately realize integrable statistical mechanics models. And I'll show just one particular example of a boost model. In the paper, we discuss more. And I'm not expert in integrability, so I just say what Vladimir told me, so I apologize if I didn't say everything correctly. So if you have integrable Hamiltonians, at least lattice Hamiltonians, with some series of integrals of motion, Q1, Q2, and so on, then at least in most of them, there exists a boost operator, which is like a ladder operator in the space of integrals of motion, which rises them. So if you commute B with integral of motion, we'll get the next integral of motion. And this boost operator is actually analog of electric field in free particle systems. So in particular, if we have this XXZ model, then it can be written as sum of local spin-spin interactions. Boost operator is exactly same Hamiltonian as extra J in front. So that's why I'm saying this is like electric field. And an interesting property of these boost operators that they have always commensurate integer valued spectrum. So all energy levels are some epsilon, which is a function of this delta, times an integer. OK. Now what we want to consider is some generic driving protocol. It could be periodic or not, where we have an integrable Hamiltonian and a boost operator. Well, we can go to the rotating frame. So in the rotating frame, we remove this guy, but then our Hamiltonian becomes dressed by this rotating frame Hamiltonian. And then we can notice that this transformation is periodic if this period t, if my integral from 0 to t of this driving amplitude is inversely proportional to epsilons, either 0 or some integer in units of this epsilon. Why? Because, as I said, spectrum of B is integer, so it means that at this particular times, this becomes identity operator, right? It's like if my spectrum of operator is 2 pi n, that in any time which is multiple of 1, this is an identity operator. Good. So in particular, one can consider two simple protocols. One is Floquet driving. And if you recognize electric fields, that's exactly what's done in experiments. So we're just considering slightly more complicated models. If you drive periodically, then you know that if you go to the rotating frame, it's how you get Bessel function in your hopping. You will drive with integral of this guy, and it's also periodic because time average is 0 and so on. Or we can consider a quench, and that's also what's done in other systems like cold atoms. If you consider a quench, you do a Peierls transformation, and then you go to the rotating frame, right? And then you also get effectively a Floquet problem in this rotating frame. But you can have other protocols as well. So now why it's good with the boost operator? Well, the reason is that now we have a similar, this Baker-Hausdorff series, and now most of the commutators are 0. And that's the general idea behind this integrable Floquet systems. Find essentially, this is an example of it, find these operators where this algebra either closes or doesn't grow very fast. So here it's clear why it's 0, because as I said, B and H commutes with H. It's an integral of motion. So it means all commutators where I put, say, H here will just give me 0. So the only commutators which are non-zero if I have B everywhere except for one place where it's H. And then this series becomes extremely simple. We can resum it. And we see that rotating frame Hamiltonian is just h naught plus sum of these phase factors times integrals of motion. And that's really nice because A, we have no heating, and B, if you think about it, we really realize we have many body energy revivals. So it's exactly like Bloch oscillations when things oscillate, and after period T, we come back. So here it's a little bit more subtle because my Hamiltonian still contains non-trivial phases. So my phases will not necessarily revive, but my energy will revive. And moreover, period of revivals is completely unrelated to driving period. So like in particular, if we do just a quench, driving period is infinite. But then I mentioned there are these magic times t, which are inversely proportional to this epsilon. It's exactly, think about this as a period of Bloch oscillations. And after this times t, I will completely revive. Good. So this is really the author of this work. So, and yeah, the summary of this quick part is that there are non-trivial Floquet protocols which lead to heating. So one can realize, and I think it's very interesting, periodic of many-body revival. So for XXZ model, I just remind again, this boost operator is relatively, it's just a particular two-spin Hamiltonian with extra electric field, if you want. And we don't have many, oh, by the way, there were actually related ideas in recent work by Lev Widmer and Markus Riegel, which was just published, who said that for particular quenches, the system remains always in low entangled state. Integrability is not enough. If we take integrable model and quench it, we will not thermalize, but we'll go to GGE with extensive entropy and so on. So entanglement will be volume law and so on. So this particular boost model, well, they essentially considered boost models. And for them, this doesn't happen because ground state always follows, sorry, wave function always follows ground state of some Hamiltonian. Here it also doesn't happen, obviously, because I have complete revivals. If there is no time to generate volume entanglement, if you want. So there are possible extensions, and that's something we don't have any results yet, but we are thinking about, to non-integrable systems, where one can realize approximate, or if you want, pre-thermalized type dissipationless regime. So of course, if the system is non-integrable, after long times, you will thermalize dissipation will take over. But it's likely that there are systems where this thermalization can be very slow. Break-in integrability is very non-trivial. And there are probably connections with counter-diabatic driving. So Dries will present a poster about this. Thank you.